We have a number of IoT devices here. These are Linux-based devices, such as the Raspberry Pi. We have an Android device, and this is the very latest in fullstack.net microcontroller that we're currently testing at the moment. That's a prototype. Now, businesses use IoT devices for things like data acquisition, power monitoring, tracking goods, GPS tracking in transport, image capture, many other applications. But there is an inherent problem. How do you know the data you're receiving is A, actually being sent from one of these physical devices and not some hacker sending the messages from somewhere else, or B, that the data you're receiving has not been tampered with? If you can't prove the authenticity of your data, then evidence of malpractice could be challenged. So we have here an SAS board, and that stands for Signed at Source, and it incorporates an accelerated cryptographic chip that on first power up generates its own unique private identity, and that identity can never be changed or copied. And these devices can be run on batteries for years, and yet it accelerates the cryptographic computation. So it makes it the perfect partner for all of these devices. This is actually a development version which our team uses for prototyping new solutions. So with the correct adapter, and I've got one here, it will actually plug onto some of these more common devices, such as the Raspberry Pi. So we plug that on there, like so. So let's go now try that. So we're plugged in, powered up, and I've just logged into the Raspberry Pi home directory. We're going to use the Factom blockchain for this demonstration because it's extremely efficient for IoT devices. And we've currently got 3 Factom clients to try, C#, JavaScript and Python. So we'll try the C# one first. I've already compiled this one. Each client has the same test, which is to create a chain. So we start with this with mono, and we're going to put some test data in. I'll just type in "this is a test," and as you can see, it then immediately comes back with the EC address. That's the public key. It's both your identity but also the payment address. You can fund that address with tokens used to commit entries to the public chain, which is what we've just done. As you can see, there is a balance there of 370 EC tokens. Now the chain has a hash, and we can have a look at that on the public blockchain, which we will do a little bit later. So we'll close that one down, and we'll try one of the other clients. Let's try the JavaScript client. Node.js. And again, this is a test. So that should come back with the EC address. Yes, it has public key and also a chain. So that's a new unique chain. What's actually happened there is that the client has offloaded the signing to the SAS chip. So it sends it up to the cryptographic microcontroller, which is it's an accelerated controller, so it's extremely fast. It's much faster than you typically get on an IoT board, and yet it can be run off batteries. It's very low power. So let's close that application, and we'll do the Python one as well. And again, we'll put in this as a test. And there we go, chain ID and entry hash. So let's have a look at the Blockchain Explorer. So I've just gone to factoid.org, which is a blockchain explorer for Factom, and we're going to paste in the hash of the chain which we created with the C# client. And if we search for that, it's come up. Click on it. And you can see at the bottom of the screen it says this is a test. That's the data which I typed in. And we can see the paying address, which is the EC address of the IoT device. So we have a proof there that this IoT device created this test message, and that will be there forevermore. It cannot be changed, it cannot be deleted, it cannot be altered by anybody. In addition to signing and identity, the signed at source microcontroller can perform a growing list of additional support functions for your IoT projects. A monotonic counter, for example, can provide a unique message number sequence independent of timestamps. This might be useful for real-time data sent to an IoT network, such as Streamer. Small SMD modules can be built into custom hardware, or as we have seen, off-the-shelf devices. And the firmware can be upgraded in situ as we gain additional blockchain support.